Hello everybody, I'm Pietro Sperotto and today I'm going to present you a recent work that we present in occasion of the European Fluid Dynamics Conference. In September, this work is titled 3D Tomographic PDV Investigation of Free Leapfrogging Vortex Rings. Except me, David Hess and Gökhan Ergin participated into the project and helped me a lot through this work. So let's start with experiment. What we have is that we perform a volumetric PTV of an unsteady flow. To achieve this unsteady behavior, what we did is simply that we take the basin, we let it get very steady and smooth and quiescent. And what we did then is that we start to measure when we started the pump. In this case, the nozzle was 50 millimeter. For performing the experiment, we used the 4 Flow FCX 5M cameras. We crop slightly the sensor in a way to achieve a slightly higher sample rate of about 160 Hz, and the final particle per pixel achieved was about 0.04. To illuminate the setup, we used an hard soft LED. So what we did is that we perform a tomographic PTV in DynamicStudio. The final measurements volume was about 200 millimeter in the streamwise direction and about 120 millimeter in the other two direction. We measured for 650 time step, but actually the leapfrogging is clearly visible only for the first 260. The peak velocity that we achieved was about 0.4 meter per second. The result, as the tracks cannot be used per se, has been interpolated by using a physics-informed interpolation. That simply means that we do an interpolation, but at the same time we enforce the continuity in these grid points. Then we also compute the pressure, and to compute the pressure, what we do is that we simply use a least square that minimize the error in respect with accelerations. And the final grid resolution is about 1 millimeter. The results shown in these pictures are the vorticity magnitude, isosurfaces and the pressure contours. What we can easily check to see if our measurements were correct is the co-criterion in the axial-symmetric plane. In literature can be found many simulations of this case, and what we saw is that our results seems to be consistent with these results. However, there is a major problem, and that is we are not able to discern the behavior of the singular vortices once they merge together. To solve this problem, we took the first time step where we are clearly seeing all the free vortices, and what we did is that we simply separated them into groups, and then for every point that was inside some threshold that we decide of vorticity isosurfaces, we assign a particle that then we advected with the Eulerian map of the velocities that we had, and we saved it in DynamicStudio as tracks by using the Python link. Here we can see the final behavior of the particles that we achieved. An interesting feature of this technique, let's say, is that it allows us to know, for example, the vorticity of every given particle of the original vortices, and this can give us insights on the strength of the vortices ring at every given instance. Here, for example, what we did is that we simply sampled the mean position of the points, and then we fit a plane into these points in order to achieve a simplified visualization of the rings while moving. But the behavior of the toroidal can be further characterized by inspecting their choreographies. What are the choreographies? Simply is the movement of the radii. Look into a plot where in in Y we have the axial displacement, and in X we have the radius increase, so the distance that we have from the axisymmetric line. And what we obtain is that we can clearly see what we would expect. So we see that initially the intermediate vortex overcome the bigger one, and then it stays outside. That's more or less consistent with what we saw in the previous video, while the red one just passes inside them, and then just at the end it envelop all the other two. On the second image on the right, instead, we see the same picture, but done in respect with a system of reference that is the center of the so-called center of vorticity. And in this case, we can see that we have this kind of closed loop movement around a certain point. Another interesting thing is to watch the total vorticity through time. In this case, for showing better what we found, we dimensionalized with non-dimensionalized the total vorticity with the value that they had at the first instant. And we can clearly see that in the first instant we have that the blue, so the intermediate ring, lose some energy. This is because it's very close to the green one, that it's the most energetic, and on the contact point they have a different velocity position, and so probably it's losing its momentum, while the red that it's sucked towards, so the first one and smaller vortices is sucked towards the center of the other two, and this increases this vorticity. While the green, as it is the, let's say, bigger one, it's almost not influenced by what the other two are doing. And then we have that at some point when the blue one goes completely over the green one, is energized by its vorticity, so it gains energy, while the red have a complete opposite behavior, losing vorticity. Yes, here it already explained. And thank you for your attention. And if you have any questions, thank you for your attention, and see you next time.